Okay, in our last part of our discussion about junction field effect transistors, there's an important modern class of transistors that are seeing a lot of use, especially in power electronics, high-frequency power electronics these days. Those are called HEMTs, which stands for high electron mobility transistors. So the basis of the HEMT structure is the heterojunction between a large and small bandgap semiconductor. So the first ones that were used were aluminum, gallium arsenide, although nowadays the more technologically used ones are gallium nitride, aluminum, gallium nitride, gallium nitride. So let's look at this band diagram and do our qualitative band lineups. Both of these, let's say they're N-type. So when we put them together, we'll maintain the conduction band offset here, but we have to line up the Fermi levels. So the conduction band offset looks like this, and we'll draw a consistent Fermi level across. And so the actual bands then will look something like this in the conduction band. So this is our gallium arsenide, this is our aluminum gallium arsenide. And just for completeness, the valence band would look something like this. So let's focus in on this area, though. The Fermi level is above the conduction band edge, which means that this entire area here is degenerately doped. Now, its width might be very small, especially when we accumulate quite a lot of carriers here. The carriers themselves will act to help screen out the field, and so we'll have a very short distance, let's say something on the order of 10 nanometers. And that means actually that this conduction band shape will act as a quantum well, and we'll actually get quantum effects, quantum confinement at that point. So what we call this is a 2-deg, or two-dimensional electron gas. And the two-dimensionality comes from the fact that this structure, in its real structure, would look something like this, with gallium arsenide and then an epilayer of aluminum gallium arsenide grown on top of it. So the entire wafer in this plane, this two-dimensional plane, would contain a 2-deg. Now, there's a little bit, I've drawn this wave function on purpose, penetrating into the L gas slightly. And that's a real effect, because we're looking at the quantum mechanical wave function in this direction. There is a little bit of tunneling that occurs into the aluminum gallium arsenide. And so if we want to increase the mobility of this two-dimensional electron gas even further, we have to make sure that there's no interaction between this tunneling tail here and the ionized dopants in the L gas. And on this side, what we do is not put any intentional doping in this layer at all. So this is unintentionally doped gallium arsenide. So it turns out that workers at Bell Labs, including my postdoc advisor, figured out that they could increase the mobility of these 2-degs by getting rid of the dopants over this region close to the 2-deg interface. So this would become unintentionally doped Al gas, and then N-Al gas over here. And so we've made the structure undoped from here to here. And by doing that, they increased the mobility in this two-dimensional plane here. So how do we use this in a transistor? Well, we have to be able to turn it on and off, but we have the benefit of when it's on, it carries current very well, very efficiently with low loss. So let's look at the side view structure over here in a minute. Okay, so over here I've drawn a side view of the physical structure of a HEMT made in the Al-gas system. So the current flow is by injection here into the channel from the source to the drain. And then the modulation comes from applying large gate voltage, just like we talked about in the MOS capacitor case, in order to turn off this channel. So by analogy, in the MOS capacitor case, we were pulling the 2-deg up against the oxide layer. Here we're actually pulling it up against the conduction band barrier formed by the aluminum gallium arsenide here. So of course, if we can deplete the 2-deg here, we can shut off the channel and turn off the current. So the current voltage would look, again, something like this, where this is increasing V gate down to pinch off there. Now I'll mention one more important thing in the case of the nitride-based materials. In the nitride-based version of this band diagram, there's actually polarization effects, electric polarization. Because the nitride unit cells are hexagonal and not centrosymmetric, they exhibit some piezoelectricity, piezo voltage, and especially along the C direction, the C axis, they'll develop electrical polarization, which means built-in electric fields that are both spontaneous as well as coming from the lattice matching, because the aluminum nitride lattice constant is smaller than that for the gallium nitride. When you match these things together, it actually produces some extra polarization voltages. And even in the total absence of any doping whatsoever, we can get very similar looking band diagrams, except bands are linear for this effect, whereas they're parabolic in the depletion case. So in modern microwave power HEMTs especially, the dopings needed are incredibly low, and a lot of the confinement potential here actually comes from the polarization effects of the crystal structure itself, instead of the band bending coming from the depletion of dopants. So that wraps up our little discussion about HEMTs. They're incredibly important these days in things like microwave amplification and high power applications because of the very, very large band gaps afforded by the nitrides. So gallium nitride is over 3 electron volts and aluminum nitride is over 6 electron volts. And that allows you to use much higher voltages than were ever possible with things like silicon and gallium arsenide. Okay, so in this short section, we've been talking about different types of field effect transistors. And the basic model for how these transistors operate and turn on and off can be seen in the sort of the original concept for a junction field effect transistor, where two opposing PN junctions depletion widths are used to turn off the channel. MESFETs are a variation, metal semiconductor field effect transistors, where a small conductive channel is made on an otherwise insulating substrate. So examples could be the use of highly insulating or semi-insulating gallium arsenide, or also silicon on insulator wafers can be used for this if the silicon can be made thin enough. And the gates in this case are usually provided by Schottky junctions. The last very important class of devices that work by the field effect that are in use especially in high power and microwave applications these days are HEMTs, and these are heterojunctions, heterostructures, where the heterojunction provides the sort of wall against which a large number of carriers can be pulled into a very thin channel in order to provide high conductivity. And then again, the field effect is used to turn off that channel by depleting it. Okay, so that wraps up our discussion of FETs, and next we'll move on to optoelectronic devices.